And welcome back, everybody, to the final workshop of day 3 here at the California Small Farm Conference. We're excited to have you here for this afternoon's workshop, which is Water Rights, Rural Water Systems, and Water Use Efficiency with Tom Hammond. We're excited to have him here. Thanks so much for taking the time to join us. And for those of you out watching, just want to encourage you all to use the chat and Q&A functions down at the bottom to say hello, share resources, tips, or perspectives of your own, or use the Q&A feature to drop in a question for our presenter today. We'll make sure to leave some time at the end of today's workshop to get to those questions. Today's workshop is being recorded. We're going to post it up on CAF's YouTube channel if you want to check it out later. And with that, I'm going to pass it over to Tom. Thanks for being here.
Thank you, Evan. I'm going to go ahead and share my presentation. Welcome, everybody. My name is Tom Hammond. I'm a licensed professional engineer in California in agricultural engineering and also civil engineering as well. Today, we're going to talk about some water rights, and then we're going to talk about some rural water systems and water sufficiency. And we're going to focus on the small scale agriculture in California component of this. There's certainly some large ag in California that we're going to skip over a little bit. Yeah, so let's jump into it. The contents of our talk today, again, like I said, we're gonna dig in on some water rights. We're gonna then go into some rural water systems and kind of take a couple parts, just dig in on those systems, and then we're gonna finish with a little bit of water use efficiency. And as we go through this talk, if you have any questions, please put them up in the chat. It'd be great to have more of a dialogue in that situation, and less of me just talking to everybody. A little bit of housekeeping to start with. Disclaimer: I'm not presenting any legal advice. I am not an attorney. Water users are encouraged to seek advice of a qualified attorney if they need to. We're going to focus on small scale agriculture water rights in California, and I just wanted to throw that out there because it is necessary, just in case. All right, let's get some context to start with. Whiskey's for drinking, water's for fighting over, famous Mark Twain quote. I think this is more and more present and prevalent as we move forward. We do live in the West. We have a hot, dry climate in the summer and a mild, wet winter. Therefore, we will probably have a resource concern every year. Additionally, in California, 3/4 of the rain falls in the north and 3/4 of it's used in the south. And so there are some water projects that have been put in place, from snowmelt diversions to aqueducts to all kinds of different things. There's multiple aqueducts running the length of California, and I think there's just one running across from the Colorado River. And then additionally, California is a first in time, first in right state. So kind of what does that mean? It means that if you're first in time, then you're first in right. It's as simple as it gets in that regard. And that's with regards to water rights. If you have a pre-1914 right, then you have a right that goes way back and predates almost everyone else's rights. Why 1914? Well, that's when the water board is established, and so you're going to hear 1914 a couple times, and that's the significance of that, is that if it's pre-1914, it was before the water board is established. If it's post-1914, it is with the water board's permitting functions. Um, Definitions. We're going to jump into some definitions just so everybody's on the kind of the same playing field with water rights. Surface water. So surface water is rain that falls and fails to infiltrate into the ground. There's a lot of different options there. It could be creeks, rivers, streams. An additional subset of that is subterranean streams and river underflow. So if you have a river and it's flowing on the surface, you can see it. That's obviously surface water. If it's flowing underground next to the river, that's also considered underflow and part of the surface water flow. Um, we'll dig into the significance of that in a little bit. Um, Watershed. Watershed's a geographic basin that's pretty much on the surface, and an aquifer is a geologic feature that is underground. It's going to be a water-bearing soil rock basin. There's two kinds of aquifers. There's a confined aquifer and an unconfined aquifer. A confined aquifer I like to think of as a bowl, and a bowl can overflow and a bowl can fill up. And then there's unconfined aquifers, which is basically like a broken bowl. Maybe it has a crack in it somewhere and it leaks out someplace, or maybe it's just totally flat like a plate and it just runs everywhere. That would be an unconfined aquifer, or maybe it drains to another water body. The other piece here is the California State Board Division of Water Rights is who you would process a water right with. And that's a common question that comes up. Um, Additional definitions. People go back and forth on the difference between infiltration and percolation. My definition for it is infiltration is water that passes through the soil in the top 6 inches, and percolation is water that passes through the soil below 6 inches. People will argue about whether it's 3 inches or 6 inches or 5 inches. We're just going to not worry about that. It's basically if it can get into the ground, it's infiltration. If it can go deeper below that, it's percolation. And then groundwater. Groundwater is water that percolated into the ground. It's pretty simple. And rainwater is water that hits a roof and is collected. Contrary to just falling out of the sky, like I always think of rainwater, the definition of rainwater for water rights is water that hits a roof and is collected. Additionally, springs. There's two kinds of springs, but springs are just basically water that flows out of the ground. There's fully contained springs and there's uncontained springs. A fully contained spring is one that is contained within one parcel boundary, one property boundary. A uncontained spring is one that flows across property boundaries, and that will be significant with rights exceptions. So water right, the ability to take water and not need a right for it with a fully contained spring, it falls into that exemption category. So does rainwater, and that's when you can collect rainwater off your roof, put it in a tank, or go so far as to put it in a pond or reservoir if you've got enough roof. And then sheet flow. Sheet flow is very, very specifically defined as non-concentrated uniform flow from the land. Pretty straightforward. Most use applications for sheet flow would be a stock pond. So a small stock pond where you just have a uniform slope that slopes into that catch basin of the stock pond. That's pretty much sheet flow collecting in there. And then some rights exceptions, groundwater. So some basins are not regulated. Most at this point are in the process of being regulated. So that's a matter of looking into your GSA and your groundwater service agencies and going to seek advice from them. Now we're going to dive into riparian water rights. A riparian water right could be present if you are diverting water from a waterway that is on the property, and you're going to use that water in the same watershed as the waterway, and the water is not going to be stored for basically stored in wet times for use in dry times. So you're not going to store the water, and it's for a reasonable use on the property. A lot of people ask, like, well, what's a reasonable use? Isn't all water use a reasonable use? And the way I interpret the way that is stated and the way that I've seen it stated is that reasonable use is not being greedy about it. If you're taking a bunch of water from everyone else, then that's not necessarily a reasonable use if you're taking it from other sources that exceeds the resource capacity. But if you're irrigating with it, you're using it for your family, that's domestic, then that's all within reasonable use. Um, what's required to establish a riparian water rate? Well, you need to file a statement of diversion with the State Water Board on an annual basis and comply with reasonable use rules. Filing that statement includes telling them how much total volume you've taken and at what flow rate and at what time of the year. And that's pretty straightforward. The water has to be flowing on your property in order to take the water. Um, if there's any, yeah, again, if there's any questions, throw them up in the chat. Yeah, Evan, thanks for throwing that up there. If you want to learn more about groundwater agencies, um, or the SGMAs, go ahead and look at that. Next in line, you got riparian, you've got appropriative water rights. Appropriative water rights are when you're diverting surface water to storage, when you're diverting water to another watershed, or you're diverting water to a property that's not adjacent to the watershed or the waterway, sorry. Um, there's two types of appropriative rights. There's pre-1914, post-1914. We're not really going to get into pre-1914. That would require, just a quick definition, pre-1914 means that you've been using the water and have been able to show proof of use of the water since 1914 or before that, and that you've been continually using that water for the duration of time from 1914 till now or before that. Post 1914 rights are more what we're going to focus on because that's typically more relevant to what we're going to be talking about. And there are two types of 1914 post 1914 rights. The standard appropriative water right is a permit followed by a license. In order to get that, you would file an application to appropriate water. Upon approval of that application, you would be issued a permit. From there, you're going to continue to file appropriate documents for about 10 years and follow the permit and basically follow that permit for about 10 years, and then you're going to eventually be granted a license. You have to show proof that you're using the amount of water that you requested, and you'll need to supply an annual water report. And there's some public trust resources that go into that, and it's a pretty big, long, involved process. But it's water; it's precious. That's more kind of the long-term way. The shorter term way with less water demand. Whoops, my slides stopped moving. There we go. Is a registration. So you can file for an appropriative water right registration. This is basically it's intended to be a fast track for smaller uses. If you have a demand that is under 10 acre feet and it's for irrigation or domestic water use, or livestock use, then you can simply register for your water right and pay a fee. You'll need to do that every 5 years and for as long as you want the water right, but it's the fast track way to obtain that right. This is kind of the end of our water resource or water rights talk. Those are basically the nuts and bolts of water rights and procuring them. Some of the resources are listed on this page. Charter Unlimited has a really good pamphlet that you can read through. It's like it's one of the few like actual readable, comprehensive water rights documents that I found that doesn't just make my eyes glaze over. And then the California State Water Resource Control Board obviously has some great facts on there for water rights. Also, reach out to your local resource conservation district or your local NRCS office. They can also point you in the right direction for if you need any water rights. If there's any questions about water rights, please populate them. We're going to jump into rural water systems now, and so throw in any questions in the chat if you do. If you don't, we'll just keep cruising. All right. Rural water systems are composed of pretty much all these things we see on the screen. They're going to have a water supply. You're going to have water distribution. Some have water processing. Some have water storage. Almost all have a power supply. and their uses are usually broken into potable and non-potable. Potable being domestic for human touch, um, non-potable being irrigation and other uses. Um, Again, going back into the context, kind of the water systems, um, I really like this diagram for just sort of showing the overview of the water cycle. So this is just the hydrologic cycle. Water's coming out of the sky, essentially it's evaporating out of the oceans, it's coming up, it's falling down, it's going into lakes, rivers. It's going to be underground. So this really highlights every possible rural water system you go for. You're going to either need a well to go underground, or you're going to be pulling it out of a creek or a stream or river, or you're going to be pulling it out of a lake, or you're pulling it from snow melt, which isn't super common. You could be desalinating it out of the ocean, which is again not common. Or you could be collecting surface runoff at the surface. But those are all going to be water supplies. A farm water system, and I did steal this schematic from Hotspot Ag. It's not a product placement. It's just I like the diagram and I like Hotspot Ag, but this would be more in the Central Valley. What you're going to see is a canal pump. They're going to have a backup system in the form of in this case, they're calling it a deep turbine VFD pump. So that's going to be a well. That's going to be a backup supply to the canal. You're going to have a pump that would be pulling out of the reservoir. The reservoir might be pushing it out to a booster pump. You're going to have a filter and a fertigation system, if you have fertigation or not. And that's going to pump out to your distribution system. You got your valve controls. You might have soil monitoring. You might have a weather station. You might have additional power on site. But this is just sort of quick rural water supply system. Um, Water supplies, I break them up into two types. There's groundwater and there's surface water. Groundwater is going to be wells or springs. Surface water is going to be streams, creeks, rivers, reservoirs, springs, underflow well. Could be rainwater. The basics here are that groundwater is going to be typically more expensive to pump, but much less expensive to treat. It's going to come out of the ground pretty clean, and you'll be able to use it pretty readily. Surface water typically is going to be less expensive to pump, but it's going to be more expensive to treat. You're going to need to filter it oftentimes more and to a higher degree. Groundwater typically comes out of the ground potable. Surface water almost always, or like very often, needs treatment of some sort to make it potable, or you need to pretty much reduce the biological content in order to irrigate with it. Um, Here's a bunch of different pictures of water supply systems. Here's a reservoir. As you can see, this one would be pretty difficult to pull water out of without clogging some sort of intake with the biological content of it. It's got some zola and some duckweed and some other stuff growing there. Um, uh, Contrasting with this system, we've got a well system. If anybody, it's hard to see the well here, so I decided to circle it. You've got a well and you've got a beige tank there. That's a pressure tank. The pressure tank allows the pressure switch to work. The pressure switch is there to allow you to have on-demand, basically pressurized water in a very reliable system there. This one looks like it pumps down to a tank, and then that tank has got a pump, or maybe goes gravity down the hill. But I think if I'm remembering the site right, there's actually a booster pump down there that then pumps back up to an orchard that is out of the picture. So you've got two power requirements. There's a fair bit going on there. This system's a little bit less complicated. There's a well, that white pipe coming out of the ground. It's got a well. There's a plate on the top of the well. That plate on the top of the well is the well seal. The white pipe that comes out of the ground, that's called the column pipe. The pipe that's coming up out of the well is called, sorry, the column pipe is the pipe coming out of the top of the seal. The casing is the white pipe. The casing goes down blank for a certain period of time where it's just solid pipe, and then it turns into screens. Those screens are then surrounded by a gravel pack. That gravel pack is the actual filter for your well. And so that's what allows the water to come into the well. There's the pump that goes down in the bottom of it, so it's a submersible pump. That pumps up out through the pipes and then pumps up to this bank of tanks. Those bank of tanks then gravity down to the system. There's an irrigation portion of it for a large garden area, and a large garden area, and there's another section that goes to a house. But these are all examples of water supplies. And then we're going to move into water distribution. I break those into two kinds. There's confined, which is pipes, pumps, which is pipes, which if you have a pipe, you're most likely going to need a pump. You'll most likely need valves and electric controls and most likely a flow meter. And then there's unconfined water distribution, which is going to be ditches. You're typically going to have weirs as control structures or flashboards. Staff gauges are going to be your flow meters for measuring flow, how you go through there. Confined systems are typically going to cost more to pump through because you're going to need higher pressures to move the water through those, but they're typically going to be much smaller. Unconfined systems are typically going to be lower cost to pump because you're typically using gravity and you're not really pumping them so much. You're bringing to a certain point and then letting them flow. However, there's some inefficiencies with those in the form of evaporation and ditches infiltrating water, but they're great for moving large volumes of water with a low amount of energy. Water distribution systems. Here's a pump. So there's a pump and motor. The blue part's the motor, the silver part's the pump. And then there's the intake and then the outlet. This is a whole big old mess of pipes. This is, I guess, the significance of this picture is that you might go out to a site and you might uh, see a whole bunch of pipes going everywhere, and there's no labeling, and there's no anything. So we can look back at the other picture and see the fact that they have little arrows and labels, and really appreciate that there's labels. You can also start to look in this picture and see different things like the silver cylinder here. That's actually a check valve. It's got Schedule 40 or Schedule 80 fittings on either side, the dark plastic. Um, then you've also got the blue box there. That blue box is a electrically actuated valve. And so that actually runs up to the tank, and the tank has a float switch inside of it that actually actuates that valve to add additional controls to the system. One thing to note is that when pipe is laid above ground like this, and it's in direct sun, and it's uh, white PVC pipe, and it's not UL rated, it has about a 10-year life cycle before the plasticizers start to migrate in the pipe, and the pipe becomes really brittle. So one of the easy things to do with this is just to paint this pipe. Paint it with a first you need to kind of wipe an acetone on it, and then you paint it with a latex pipe or with latex paint, and it will prolong the life of the pipe significantly. That's just kind of a good maintenance practice. The darker pipe, the Schedule 80 pipe is dark gray. That's usually good for about 20 years in the sun before it starts to migrate. But again, it's easy to paint the pipes and extend their life cycle. More water distribution. This is a valve box. Inside the valve box, we've got a solenoid actuated valve. So there's a red wire, there's a white wire, so there's wires going to it. That's what controls the solenoid. Downstream of the solenoid, we have a filter. Usually like to see the filter above the solenoid valve because it doesn't take much for the solenoid to get clogged underneath here, and there's a little tiny plunger, like a grain of sand can cause it to fail. And then there's this unit on the downstream side of it. This is a pressure regulator. It's regulated to a specific pressure because the downstream side over here has some sort of sensitivity. In this case, it's drip tube, so they wanted to keep it from seeing too high of a pressure. Other systems, this is an example of a great system as far as its labeling. It's not painted, which is it's okay, but it means they won't last quite as long. But it really highlights the pressure tank and the pressure switch. So this is a pressure switch. I'm not sure if you guys can see my mouse, but I'm going to move my mouse around the little gray box here. That's the pressure switch. This is a pressure tank. Pressure switch determines when to turn the pump on and off. So that's the control unit. And then it moves out from there. This is a flow meter. This is one style of flow meter. So we have a totalizer right here. That's where you'd read from the totalizer piece. And then this is a dial read unit. And this little tiny red dial is there for very low flow. So during very low flow, this would be spinning. And then the dial will read out to the gallons per minute moving. Contrasted with this other very typical meter, it has a totalizer here, and then it also has these multiple dials. The little red dial here is for detecting super low flow, These other dials, you'll need a stopwatch and you'll need to count the times it goes around or count until it goes from basically you've got the it's like ones, tens, and 100s here. Or point ones, ones, and tens, I think is what it really is. And so as they rotate around, you just need a stopwatch, and then you can actually determine the instantaneous flow. Most of the time, these meters are good for just totalizing. Also, this black cable that's coming, or the not black, the gray cable that's coming out of it, this is a pulse. Um, Pretty sure it's a pulse sensor. So it's inside the meter, there's a little magnet. That magnet forces a little pulse to go across the wire. The wire then goes to a digitizer, and then that'll you can put that onto a data logger. And that data logger then can log the totalized amount of flow for you if you wanted to. So this is kind of a way to low tech digitize your analog system. This is a picture of a motor and a pump. Um, what do we want to talk about here? This one's in the dirt. So this, I guess that's one thing. We want to try and keep our pumps and systems out of the dirt, because if they're in the dirt, they get broken quicker. If you're looking to try and size your motor or trying to figure out what your motor is, that's going to be on this nameplate right here. And then on your pump, if you're trying to size your pump or figure out what your pump is, it's oftentimes on the face we can't see over here. There'll be a little placard with that pump type on it. And so you can look at that pump. It'll provide the make, model, serial number, oftentimes the sizing or the impeller sizes. So if you need to replace things, you can go ahead and pull the numbers off there, and then you can also look at the motor and see what the overall motor size is. Does everybody know what this little blue thing is here? So these are really important. This is an air vent. You want to put an air vent at the high point on your pipeline. So if you have anywhere you have a high point in your pipeline. Additionally, anytime you have a pipe that is getting full and getting empty and getting full and getting empty, kind of like when you're irrigating. So every time you go to irrigate and let's say everything flows out through the drippers at the end and your pipe gets empty, it's gonna get full of air and then you're gonna push water back through it. You want to have an air vent at the end of your line or at the high point in order to let the air out of it. Otherwise, it will just go out your drippers too. But if there's any kind of high point, it can constrict the flow in the pipe and then it'll force your pump to work harder. And then you won't be getting that even distribution uniformity you're wanting to get to your plants. Water treatment. We've got two kinds. There's physical and there's chemical. Physical water treatment is typically filters in the form of screens or discs or sand media or reverse osmosis if it's really bad. And then chemical, which is usually softening or iron reducing or pH balancing or bicarbonate dissolving, which would be like sulfur additions. Um, some of the water processing systems. This is a standard small screen filter. Underneath the neoprene sleeve here, there's a screen, and the water flows in. The particles get trapped in the screen, and the water flows through and out. And then it has a little twist clean, automated cleaning system. You open the valve, twist the top, and it flushes the screen for you. This system is a disc filter system with an automated flushing system. So inside these big pods, there are discs. Those discs have a certain micron size passing them. These are great for high biological content. So with high biological content waters, such as surface waters, like you're pulling water out of a pond, you want to filter with as big a surface area as you can get. The biggest surface area you can get is always sand media, but sand media has pretty strict restrictions on flow rate through them. And with smaller systems, the disc filters are oftentimes better because they're rated for smaller systems. And the sand media tanks don't usually get down too small. So within the disc pod, within the pod, there's a bunch of discs, and the water travels past the discs, and it collects algae on the outside, and then it gets backflushed. So inside this gray box here, this is an electronics box. There's basically a little pressure transducer, and that pressure transducer you set to a certain pressure differential. So when the pressure on one side of the filter when the pressure differential across the filter exceeds this, usually around like 6 to 8 psi, then it'll run through a backflush cycle. and it'll flush water out these pipes. Another thing that's interesting about this site too is the color of this pipe, this orange pipe here. This is the pretty sure this is a back flush pipe here, and it's super orange, and that's usually indicative of high iron content waters. Just as a side note, and there's that another air vent right here, and this is a super cute little Sam Media filter. Um, This is a little bit older style, but inside of here is full of sand, and the water goes into the top and then flows downwards and out the bottom. And the water has to pass through the sand. And so as the water passes through the sand, it filters out and has a massive surface area to filter out all kinds of small organic particles. Once In this particular case, there's no automated backflush cycle. You just need to open this valve up on occasion, not too much because you'll blow all the sand out of here, but just a little bit, and it will then push all that algae that's accumulated on the top of the filter out and let you backflush the system so that you can get better flow through here with less pressure. All right, let's jump into water storage. We've got reservoirs, tanks. So yeah, what are all the ways you can store water? You can store them in tanks. You can store them in reservoirs. You can store it in the ground, like on-farm recharge. Um, that's that's probably the biggest reservoir and tank around. Um, but if you're in an unconfined aquifer, that can be kind of difficult because you might not get it back. Um, Here's a simple tank bank system. So we've got 5,000-gallon poly tanks. These are actually storing rainwater that was caught off an adjacent roof kind of behind these tanks. And it goes down to a little pump station. This little pump station then pumps to the irrigation system. Um, this is in a resource constrained area where there's higher water use during the summer and less resource availability. And so um, that was kind of the big benefit of this system. It was a grant funded system because of the resource concern and the water use. But yeah, we can see all the parts of the system. We've got our pressure tank, we've got our pressure switch down here, we've got our pump, we've got our filter, and here's our electric control box here. Another water storage reservoir. Another water storage, large water tank. This is a 200,000 gallon tank. Again, storing rainwater off of a 10,000 square foot roof. And it then pumps back up to irrigate crops up high above it. And this actually irrigates livestock as well. Power supplies. So you can tie into grid power, you can tie into solar power, you tie into diesel. I like to joke that when you burn diesel or gasoline or propane, you're burning dinosaurs. My kids get a kick out of it. But then there's also water power. So some examples of water power would be taking water let's say out of a stream at a higher elevation and running it downhill and using gravity. And you can run that down and then you can run it into a ram pump to then pump up higher. So you put a larger flow into the ram pump and you get a smaller flow at a higher pressure out of it. Um, Dinosaur power diesel engines, there's certainly quite a few direct drive diesels. They're usually on larger systems. I haven't seen too many on smaller systems. Solar power systems are are fantastic. If you're just irrigating crops and you have a decent supply of water, and you're irrigating during the day, solar is a great option because you can size your system to meet your peak crop demand and just literally use the sun. Um, it's it's a great way to go. You can definitely do three-phase on solar. You can do single phase on solar. So when we talk power supplies and phases, along in the not too distant past, solar was seen as only able to power up to like 5 horsepower, and you couldn't get a solar system to power anything more than a 5 horsepower pump. There are systems now powering 30, 40, 50 horsepower pumps, and They might require some battery to kind of help get that inrush current to work out with the initial start of the pump. But the it is totally possible to use solar to power some pretty decent size, like some large pumps. Especially, and it works really perfect for me in my mind for irrigation because the sun's out, you want to be there to irrigate. It's all super simple. Here's some examples of grid tied power. You've got your main circuit breaker up on top. You've got your smaller circuit breakers down on the bottom. If you want to turn your main power off, you turn it off up here. If you want to just turn off, in this case, it says reefer, you just turn it off right here. And there's the well house, turn it off there. Um, Here's a little tiny solar pump system. This was a little half horsepower pumping system. It was this solar panel plus a car battery, and it was to empty out the bottom of this reservoir as the reservoir needed some repairs done. We're going to jump into a quick case study with the goal of trying to figure out what the cost of water is in this case. So it's a homestead study, or it's basically a case study on homestead. So the water supply is a 5-inch well. It's 300 feet deep. The pump is set at 260 feet. The water is at 200 feet. So that means that when you're pumping, you're going to pump from 260 feet, but the water is really at 200. So if it draws down to 260, you're going to not have water anymore. So usually you want to set the pump significantly below your water table. Our pump, how do we size the pump? We're going to use the water horsepower equation, which is the pressure in feet times the gallons per minute flow rate divided by 3690, and that's going to give us our water horsepower. We're going to divide that by the efficiency of the system. In this case, I made a broad sweeping assumption of an efficiency of 50% or zero point 0.5. So that's going to give us a rounded up to 2 horsepower power demand for that pump. We're going to power this with grid power. Water distribution is going to be through a pipe. We're going to size that pipe to under 5 feet per second, which is going to provide a low friction loss. You may pay a little more for the capital cost up front with the pipe size being larger, but you will pay a lot less in needing to pump it. And oftentimes there's a return on investment for sizing pipe to be in that 2 to 5 feet per second range to optimize the efficiencies of that pumping system, of that distribution system. We're going to need a booster pump at our tank, and that's going to be 20 gallons a minute. We size that 20 gallons a minute based on the water use demand down lower, and our pressure from there is going to be 100 feet. So that's going to be it's a 1 horsepower pump. One of the reasons that I like doing a well to tank to booster pump is that it reduces the need for your well pump to work as hard to put water to where it needs to go because it just needs to pump pretty uniformly all the time to your tank. That's going to increase the lifespan of your expensive submersible pump that's down in the bottom of your well, and it's going to put more stress on your booster pump. And your booster pump is on the surface, which means it's very easy to work on. You can swap out the seals, you can swap out impellers, whatever you need to do. It's right there on the surface. It's a lot less expensive to work on those, and they cost less in general. And so it's better to put the demand stress on them of like of moving all that water around, and use a tank as that reservoir and buffer for your water supply from your well. Water storage. We're going to put a 8,000 gallon tank in. Water use. The water use is going to be domestic, potable for human use. There's one house and plus a garden. The house's daily demand is about 200 gallons a minute. 200 gallons per day. That's high for some places. That's low for some places. It really depends, but that's obviously an average. And that's a 4-person residential home average. That comes out to 73,000 gallons a year. And the average demand of a house is usually 5 to 10 gallons a minute. So I put it at 10 gallons a minute. A garden, it's going to be a half acre a drip. It's going to have 4 irrigation sections. So 1/8 acre sections you need to calculate both instantaneous demand and total demand for the year. The instantaneous demand is comes out to about 20 gallons a minute, and the total acre feet per year based on the ET of Sonoma County, Mendocino area, as region 4, comes out to somewhere between zero point 0.4 and zero point 0.8 acre feet per year, which I went with the zero point 0.8 acre feet for the next calculations, which is about 290,000 gallons. Um, so what's the cost of water? Cost of water is the capital to build it plus the power to operate it. The capital cost is around $60,000. So that's going to cover your well, your pump, your tank, your booster pump, your pipe distribution system, and the power supply. So bringing grid power to all of that system. The average life cycle of that system is going to be about 30 years. The well itself will last longer. The submersible pump is going to be 10 to 20-year life cycle. The booster pump will have a 10 to 20-year life cycle. So I didn't factor those in to this calculation because I was trying to keep it simple, but I just wanted to be explicit about that. It comes out to about 2,000 a year. So the operational cost is the well, is the cost of pump, basically just the power cost, well and booster. Power cost comes out to about $313 a year, which is not very much. So the cost of water, the cost of the actual water is about 0.7 cents a gallon. So it's less than a penny a gallon, um, which it's like, well, that's not very much. Like, why would I care if I'm very cost motivated, why would I care about like such a cheap available resource? So um it really comes down to if you're trying to grow something, it's going to be the yield function of why we would want to jump into water use efficiency. All right, so that's case study on the homestead. Factor in the cost of water. Yes. How does water quality treatment factor in the cost? So I didn't factor that into this homestead study. But water quality treatment can be a large cost for sure. I'm sorry, I'm reverting to the chat. The chat says, how does water quality treatment factor into the cost of water? Um, that's not factored into this homestead study. I'm assuming that the well water is potable and adequate to consume. It's not higher in iron. It's not It's not high in salts. If you do need to treat for those, the costs vary significantly. So if you need to treat for iron, for instance, you're going to need to put in it's essentially a chemical filter. Um, and if you need to treat for other types of ions, if you're trying to reduce salts in the water, there's two solutions. You can try to remove the salts, and there's technically three ways to do that. You can deionize the water. You can boil it, basically, desalinize it, and then you can reverse osmosis it. They all have their pros and cons, but that's the only way to remove salts from the water. Most of the time, water treatment will sort of dilute the water to a certain potable point, in a lot of instances. But the cost of water treatment will like it can go very high or it can be very low. I hope, does that answer your question? Excellent, thank you. Are there any questions on rural water systems? I'm going to jump into water use efficiency. All right, so water use efficiency. This is the definition of water use efficiency. I like equations. I'm an engineer, so I feel like this is the simplest way to put it. But it's water use efficiency is literally just crop yield divided by water used. Um, I also feel like this is a very simple and narrow view of a very complicated subject, because crop yield is a complicated subject just in its own right, and water used is a complicated subject. So I'm going to kind of try to digest this with water use efficiency strategies. So if you're focusing on crop yield, you can do that with optimal water availability. Like achieving optimal water availability can be done in a multitude of ways. One way is to simply look and feel your plants. Like, does your plant look stressed? Does your plant not look stressed? Does it need water? Does it need something else? Other ways to do it for specifically for water, we're looking for at leaf bombs. We can look at soil moisture. We can do ET sensors or ET modelers. There's dendrometers. There's NDVI imagery. There's there's a multitude of technological solutions out there for people to use, and I'm a big believer in appropriate technology for appropriate scale and placement. If you're a market gardener, you're probably not going to be using dendrometers out there. You're probably going to be going more with the plant look and feel and going just intuitively knowing like, okay, I irrigated you a little while ago and you're looking a little stressed. Maybe it's not water, or oh yeah, I didn't irrigate you. We do need to work on that. If you're maybe you've got like a fairly large orchard or vineyard, then the dendrometers might make more sense. And then same thing goes with the NDVI imagery. If you're on the coast growing vegetables, the NDVI imagery almost is not very useful because the fog really the fog comes in, blocks. You don't get imagery. You get imagery like maybe once a week, and so you're making guesses on weekly information, and your plants are going to need a much higher frequency and interval of care to. So that's not going to work. But let's say you're in the Central Valley and you're growing an orchard. That might be a fantastic use for that because you're getting consistent data inputs, and your inputs can be a week late and still not have a huge impact sometimes. Sometimes obviously it can't be a week late, but within reason there, it's much more applicable. Another thing is to focus on crop yield with optimal soil biology. And my simple phrase is just more biology is more better. Um, I feel like it's yeah, so good biology within your soil can reduce your plant stress. Good biology within your soil can just produce more crop. There's all kinds of benefits there. There's that it holds more water. It like biology is like 70% water. So it's like the study of water interaction with the world. And so the more biology you can have in there, the better. You can focus on water delivery with optimal water. Sorry, you can focus on water delivery with optimal water delivery. I think I meant to say water use with optimal delivery. So what's that going to look like? That's going to look like drip or micro sprinklers, subsurface drip. That's also going to tie into distribution uniformity testing. So how evenly are you spreading that water across the area you're trying to irrigate? If you're flood irrigating or furrow irrigating, the um, how fast are you getting to the end of the line so that you can get that water to infiltrate all the way down uniformly, or are you getting a whole bunch at the front or you're getting like not very much at the beginning and it's all going to the very end of the field and sinking into the field. Um, but yeah, you can focus on dosing your exact plant with a dripper. Um, you can also focus on growing crops in climates that are suited to the area. Um, I don't think I need to say anything about that one. Focus on water systems, maintenance and control. So you can focus on uh, deploying remote sensors. You can focus on deploying timers, or you can fix leaks. You can install flow meters. There's lots of different water use efficiency strategies that are accessible at all price ranges and all functions. I'm going to dive into distribution uniformity testing because I think it's a valuable thing to do that doesn't take a whole lot of time or money or effort. So distribution uniformity testing is simply testing for how uniform your irrigation system is spreading the water across your irrigated lands. Um, and it's very easily done in vineyards. You can just use a calibrated beaker, hang it on the dripper, and the drip tube's hanging up above the ground. It's very easy. It's a little tougher to perform in row crops. If you have row crops with drippers, and it means you got to kind of elevate the dripper up and get the cup under there and measure it. It's a little bit harder, but it is doable. And then if you've got flood irrigation, it's pretty hard at that point because you're looking at multiple soil probes and you've got to like or dig a couple holes maybe. That's another way to simply do it. But look for how far that water's going down into the soil, and is it getting into that root zone you're looking for. What's the purpose of this of distribution uniformity testing? one thing it can do is highlight pressure deficiencies. So if you have a drip system and you are um, there's a section of your plants that are not thriving. It might be because there's a pressure difference there. There might be because there's a clog somewhere. So it could highlight some operational issues. It can highlight some key functions that you can then take action on to help get that system back up and running. And the cost of water is not very high, but the cost of not producing is high. So the distribution uniformity testing can help your production of your crops, and also lower your cost of water by reducing the pumping costs, and obtaining more uniformity. Some of the resources for water use efficiency. Yeah, reach out to your local RCD office, reach out to your local NRCS office. There are some California programs out there in water use and efficiency. Um, are there any questions on water use efficiency? With that, I think I'm a little early in finishing, but um, are there any further questions? I know we covered kind of some denser topics and kind of brushed over. A lot of these subjects are a lot easier to point out in a field like as you're walking through and get your hands on them. But I was trying to pull those pictures up to kind of highlight some of those pieces. Are there any areas that we want to just dive in and do a deep dive on? Does anybody have any specific questions about maybe their systems or other systems they're working in? Seeing any questions pop up. I just really want to thank you all for your time. Um, this has been challenging. I'll give you that basically talking to myself for the last 45 minutes. Thank you, Evan. I really appreciate I appreciate your hosting. Oh, I did get it. There are a couple questions, it looks like. Um,
In the Q&A there or in the chat?
oh, I see in the chat. Where is the
Okay.
Q? Is there a Q&A
There,
specifically separate from the
there
chat?
is, yes. If you go down to the bottom of your screen, there's a Q&A function. If you click that, there's a couple questions in there. I can read them out if you'd like.
Um, how about I answer the questions in the chat box real quick? Does
Sure.
that work? Is it safe to use rooftop collected water on vegetables? Um, so strictly speaking, rooftop water is non-potable. So rooftop water would fall into the category of all non-potable water. Can you use it on your vegetables? You are not technically supposed to use non-potable water in washing vegetables. However, irrigating vegetables is usually um, there's a line there that I'm not like, yeah, I don't fully know where the line is that crosses there. I know you're not allowed to wash vegetables for sale as washed vegetables without potable water. However, um, drip irrigating vegetables with rooftop water, I've done it, but it doesn't mean I wasn't growing for the public. I was growing for myself. So there's a line there. Um, let me know if there's more to that question, and I can try to answer more fully. Next question: do you have any examples of rudimentary spring boxes that can be placed in springs? Um, yes, I've seen a really wide variety of spring boxes. Everything from a 5-gallon bucket being the simplest, all the way up to a fully constructed concrete box. But the thing with springs that you want to be careful with is that you want to dig the spring out to the point where the water is actively flowing into your spring box. Um, and that's important to kind of contain it. There, if you look up some of the NR or the Natural Resource Conservation Service resources, there are some good details in there of spring box diagrams. I can't pull them up right this exact moment, but if you dig into the NRCS resources, there are some. I'm not sure if you're familiar with they call it the EFO tag. It's basically their electronic. It's their catalog. It's basically their catalog of conservation practices, and within that, I'm pretty sure there's a Springbox one that you can get some good details out of. Next question. I put this in the Q&A. Put this in the Q&A. Okay, so shall I read it out? Are water rights or permits required to capture water from ephemeral streams, creeks, slash runoff? Would it depend on whether or not the ephemeral flows terminate at a non-ephemeral water body? Um, Strictly speaking, an ephemeral stream, creek, or runoff would be surface runoff. And so technically, yes, so it would be a surface water right. So you can collect from an ephemeral stream if it is flowing. Let's for instance, you have an ephemeral stream that flows across the property that you're part of, and the water's actively flowing. You can take that water out. You're technically supposed to file a statement of diversion for a riparian water right to take that water. Um, there's yeah, that's kind of that's like the technicality there. If it's an ephemeral stream that flows adjacent to the property that you're using the water on, then you would need an appropriative water right to pull it to take that water. If you're taking that water to storage in wet times for use in dry times, then you would also need an appropriative water right. It sounds like that would be a good use of the water appropriative water right registration um, if you wanted to store it or wanted to, um, yeah, if you wanted to store it or use it off site from the riparian property. Let me know if
Right.
that answers the question or if there's more questions on that.
Sure.
Okay, I'm
Another
gonna stop.
question.
I'm gonna go ahead. Should I stop my share then?
Um, yeah, sure. You can do that. So another question someone asked is
Oh,
if I
there they
want to buy
are.
a piece of property with no wells that is previously undeveloped, how do I find out in advance if I can drill a well? Are there places in California where you can't do this at all?
That's a great question. The quickest answer I can come up with is specifically in Sonoma County right now, there is a well drilling moratorium in place. So if you were to buy a property without a well and you wanted to drill a well, you could file to drill a well, but they would not grant it until the moratorium is over. That's kind of a example of a temporary thing that is occurring because they got sued. Most of the time, you can go to a county's permitting website and look up well permits, and then you would look up well permits and you'd look up well permitting requirements. Um, Most of the time, you just need to fill out a well permit or well drilling permit, and then you would process the well drilling permit, and then you can go ahead and drill a well. Specific to Sonoma County again, in order to do that, you need to contact a well driller, and the well driller actually has to file that permit, that well drilling permit with the county. And they do that on your behalf for your property, and then they can go ahead and drill a well. Um, that's probably the easiest way to do that. And yeah, yeah, you could definitely, and if for some reason it's an extremely remote county that maybe their permitting office isn't um um doesn't have a lot of online resources, you can definitely give them a call and ask them. I've had to do that in like El Dorado County actually, where it, a phone call was worth a whole bunch. It was really good. Um, and the next one, I think the next one was also put in the chats. Um, and then the next question down, Anona, how can I do due diligence when buying a property on an existing well? How do I find out if it is likely to run dry Are there people who specialize in helping buyers access water on properties and give you estimates
Assess
of how much?
water.
What was that?
Helping buyers assess water.
Oh, helping buyers assess water. Thank you. And give you estimates of how much it will cost to put in a well water system. Um, yes. Uh, Great question. Again, doing due diligence on a property is super important. Um, because if you buy a property that doesn't have any water, that's going to be a problem. Um, the easiest way to do due diligence on a well is to do a pump test. A pump test involves contacting a well pump company or a pump company. They don't necessarily have to be a well drilling company. They could just be a pump company that does pump tests. And what they would do is pull the equipment, or they'd either pull the equipment out of the well, or they would use the equipment that's in the well and they would perform a pump test. Doing a pump test involves pumping as much water as they can for a certain duration of time. What that will tell you is how fast the well draws down, and the drawdown, how the speed with which the water goes down, will help you determine the capacity of that well and also the rate with which it recharges. And so what you would do is you'd put a sounder in the well, and then you would pump it, and then you would watch the water table move around. Additionally, when they're doing that, they can test the pump that's in place. They can check the continuity of the coils, and they can check to see if the pump is in moderately good condition or not. Um, the um, that's one method. So that would be the most physical method. It basically would be like go out and just physically test it. What it's not going to tell you though is if it's seasonal. So some wells in some regions are going to, or basically they go dry in the summer and they're wet in the winter because they're very affected by the rainfall. And so in that particular instance, you might want to contact a hydrogeologist, and I've done that in the past. The hydrogeologist is going to take a look at the underlying geology of your site and say, "Oh, yeah, you're out on the coast in a fractured sandstone aquifer that basically just takes in the rainwater, and it goes right through it, and it might dry out in the summertime, it might not." Um, or they might tell you, oh, you're in a huge basin. Like this is never gonna, it's very rare this is ever gonna go dry. Um, or you're in a fractured volcanics region that uh, is really spotty. It's like you're not really sure. If you wanted to do a really long-term test on it, to really kind of guarantee the cycles of it, you could put in a well sounder on that well, and you'd take readings of the depth to water from the surface for maybe an entire year. Um, I know that's not really realistic when you're trying to buy a property because you can't be an escrow. I mean, I guess you could be an escrow for a year, but usually it's much shorter. So to maximize that, it would be contact a pump company, have them come out, do a diagnostic on your pump and your well, by pumping it and pump testing it. They might pump it for about 8 hours is a pretty normal pump test. And then in addition, contact a hydrogeologist to do an assessment of the geology on the site. I think that should give you a pretty good idea. A lot of times hydrogeologists are also going to know like, oh, yeah, this site's known, or this whole region's known for not having much water. Um, All right, next one down. I'm looking to put an old well into service, but not sure where to buy the submersible pump. I had the well tested and it produces 6 gallons a minute. It's 1,100 feet deep and water is at 150-ish feet. Wow. It's a 4 to 6 inch wide hole that is sleeved. I'm in San Diego, but willing to buy online. Any advice would be appreciated. Um, That's interesting. I'm getting stumped on the 1,100 feet deep, but the water's at 150 feet. Um, and it looks like maybe there was a exterior casing and then an interior casing was maybe put in, which tells me that maybe the exterior casing failed at one time. Um, or maybe that's just what you're saying is that the hole The hole in the ground has the casing in it. So the sleeve, the casing piece is actually that's what's holding the well open. Um, uh, so to answer your question directly, if you look up performance pump, they should be able to sell you a submersible pump. You're going to want to get it sized appropriately. So the sizing of it would be you're going to need to use that water horsepower equation, and then get your total depth and pressure you're going to want to pump, and your flow rate, and multiply those together, divide by 3690, and that's going to give you water horsepower. You're going to want to take that and double that number at the least, at pretty much minimum, and then that will give you the amount of horsepower you're expecting. If The other thing is 150 feet of metal pipe is going to weigh a lot, and you're going to need some specialized equipment to get that down there. So you probably need at least an A-frame, if not like a rigging truck. So I'm not sure if you have that or not, but it might be worth consulting a well pump or a well pump company basically in your region to do that for you. But that would be that's my answer on that one. If you have further questions, please let me know or reach out. Will the presentation and Q&A be available online?
And I can answer
Um,
that one. So
yeah,
yes, this recording is being this workshop is being recorded. We'll post this on CAF's YouTube channel, so you can check it out after the conference. We'll send a link out to everyone who is registered. And I believe that's the last of the questions. So unless there's anything else, I just want to say a big thanks to Tom for being here with us, sharing your expertise on all things water.
my pleasure.
And
Yeah, no, this is great. Thank you all for listening in. I really appreciate it.
great. Well, thank you all for attending, and we hope to see you tomorrow back at the conference. And good luck with your water. We'll see you guys soon.
Absolutely.